Okay, let's dive right into this explainer. On the surface, what we're looking at today seems like a simple Class 1 math chapter about shapes. But honestly, it is a total masterclass in early pedagogy. We're going to see exactly how this curriculum brilliantly tricks kids into learning physics. It completely blends storytelling, logical reasoning, and hands-on experimentation to teach the fundamentals of geometry and motion. As you'll see, early education isn't just about rote memorization anymore. It's really about helping kids make sense of the physical world around them. Now, we are skipping the standard agenda today to start with a high-stakes survival story. It acts as this incredible pedagogical Trojan horse. Before introducing a single math term, the chapter asks a literal life-or-death question. How does a little lamb escape a hungry wolf? By gripping the young learner's attention with a narrative right out of the gate, the concepts of shape and motion become instantly relevant. They aren't just abstract ideas on a chalkboard, they're tools for survival. So here we see our protagonist, a little lamb who's intercepted by a hungry wolf on the way to visit her grandmother. She cleverly begs the wolf to let her grow big at her grandmother's house before being eaten. She negotiates this temporary stay of execution, promising she'll be way bigger and tastier after her visit. The wolf agrees, and the lamb reaches her grandmother, but she knows, and the kids reading know, that she has to face that wolf again on the journey home. The tension is set up perfectly. Now, what's really amazing about this is the grandmother's genius escape plan. She packs the lamb into a Dolac, a traditional cylindrical drum, to send her speeding down the hill to safety. The Dolac rolls rapidly past the confused wolf, carrying the lamb all the way home while the wolf just runs fruitlessly behind it. It's a great story, sure, but more importantly, it's a completely visual demonstration of mechanics. Which brings us to Section 1, the rolling Dolac escape. Let's see how this whimsical storybook escape turns into a foundational geometry lesson. The absolutely crucial point here is that the textbook uses this dramatic chase to prompt kids to naturally analyze shape and inclined surfaces. The source material explicitly tells educators to let the children reason out why the Dolac rolled. It doesn't just hand them the answer. It asks them to consider the relationship between the cylindrical shape of that drum and the sloping, or as the text playfully calls it, sloppy, inclined surface of the hill. Without even realizing it, these kids are doing actual physics. Moving right along to Section 2, long versus round shapes. This is where we start defining the physical world. To do this, the chapter introduces a game where kids sit in a circle with a character named Vidya Didi. They take turns naming one long object and one round object without repeating what others have said. It's such a brilliant way to gamify learning, right? The kids are actively looking around their immediate environment, scanning for long items, like maybe a pencil, and round items, like a ball. And this exercise illustrates how children begin to classify their world by zeroing in on specific spatial dimensions. For long objects, they start focusing on dimensions like how tall or wide something is. They are basically taking the chaotic physical world and mentally sorting it into manageable categories. Understanding long versus round is literally step 1 in grasping 3D geometry. Okay, this is perhaps my favorite part because it's all about logic. The curriculum encourages kids to explain their own reasoning for why an object, like a tumbler, fits into either category. Some kids might say a tumbler is long, while others might say, no, look at the top, it's round. Both views are considered valid. It teaches them that shape isn't always binary. It depends entirely on how you orient the object and what specific feature you're looking at. It's early critical thinking at its absolute finest. Now we're jumping into Section 3, to roll or to slide. Here is where we see those physics concepts really put into action. Look at how this illustration sets up an everyday playground as a literal laboratory. Kids are visually testing which items tumble down the slide and which glide smoothly. You've got a child going down the slide, demonstrating a sliding motion. Another child is kicking a round ball, demonstrating a roll. The playground frames scientific observation in a way that makes roll and slide instantly recognizable to a child's everyday lived experience. Then, by introducing the board game of carom, the text provides another highly relatable real-world example, this time of flat sliding motion. In carom, the flat disc-like shape of the striker ensures it glides smoothly across the board rather than tumbling over itself. It's a localized, perfect example of sliding logic that so many kids already know and love. Building on that, students are challenged to look at pictures of different objects and assign an R for rolling and an S for sliding. This puts their brand new observational skills to the ultimate test. They literally have to mentally simulate what would happen if they pushed the object on the page. Would it roll smoothly over a curved surface, or would it just drag along a flat edge? And that leads us to the big aha moment in Section 4, shapes that do both. This is where we throw a massive wrench into the rules. We ask the students to find the exceptions hidden right there in their own homes and classrooms. Finding things that can do both requires a much higher level of spatial visualization. The student has to realize, wait a minute, an object might have both curved and flat surfaces depending on how I hold it. Now, check out this project work chart. It pushes kids to methodically track and test these objects. This is literal data collection for first graders. A water bottle, for instance, if you lay it on its side, it rolls, but if you stand it upright on its base, it slides. A matchbox? Strictly a slider. A ball? Strictly a roller. By filling out this table, students are conducting small-scale physics experiments, moving from gut intuition to actual structured evidence. Finally, we reach Section 5, Math in Everyday Play, where theory meets the toy box. Rather than just pointing at shapes on a piece of paper, the book tasks children with literally building towers, houses, and robots using specific shapes in clay. This is engineering at its most fundamental level. They quickly realize that a rolling object makes a terrible foundation for a tall tower, but a flat, sliding object works perfectly. They are applying their geometric knowledge directly to construction and playtime. So, the crucial point we take away from this pedagogical masterpiece is that learning here isn't about blind memorization. It's about discovering the physical why behind everyday objects. It's about understanding why a wheel works, why that Dolac drum rolled away from the wolf, and how the specific features of an object completely dictate its function in the real world. So I'll leave you with this. Take a moment to evaluate your own surroundings using these exact rules. Look at the device you are watching this explainer on right now. Would it roll or would it slide? Does it have flat edges or curved ones? Next time you pick something up, consider the simple, hidden brilliance of its shape. Thanks for diving into this with me, and keep observing the world around you.